Good evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest video. And in this video, I'm going to take a look at, does summer predict winter? Here are a couple images of course, the sun shining brightly on the particular day here on the left, indicative of a summer sun perhaps. And on the right, we see the sensible weather that typically occurs in the winter season with this snow falling. Is there any relationship between how the summer turns out and that subsequent or following winter? Let's go ahead and delve deeper into that tonight. First, with my opening thoughts. I conducted research as part of my master's thesis, investigating the relationship between North Atlantic hurricane season, the accumulated cyclone energy values, the ACE values, and the following East Coast winter season, extratropical cyclone frequency, as well as the strength of these extratropical cyclones. And my one premise that I really kept in mind when I did my research for my master's was that certainly there must be some form of balance that occurs between atmospheric energy. Of course, you have two types of main energy, one being potential or available energy versus the kinetic energy or energy of motion. And so the main premise here is the balancing act, the equilibrium established within the atmosphere. In this first case, it was cyclone frequency, how much potential energy was being used up in the North Atlantic hurricane season, how much potential energy was left over for that following winter season for extratropical cyclones or nor'easters to tap into. And simply put, for every action in nature, there is an equal and opposite reaction. And this was coined through Sir Isaac Newton's third law of motion. The atmosphere is still going to work in the same regard as that Newton third law of motion. For example, excessive heating at the equator is typically balanced out by excessive cooling at the poles, resulting in equilibrium being established. Mid-latitude cyclones with frontal boundaries are created, as well as warm season storms such as hurricanes. And what these cyclones do, whether we're talking extratropical mid-latitude cyclones during the winter season with various air masses, as well as the warm season hurricanes, they act to redistribute heat from the equator towards the poles. And have you ever heard someone say, for example, it is a hot summer, that must mean the following winter is going to be a cold one? You may have heard this before, and it could be the other way around. Hey, it's a cool summer, the winter's probably going to be mild. Stuff like that typically occurs. And I do believe that hotter periods are eventually balanced out by cooler periods for a specified location. And a more recent example of this occurred during the 2022-23 winter season, which was unusually mild across the eastern U.S., followed by unusually cooler temps here in the spring of 2023. So we had milder winter last winter in the eastern U.S., and now we're seeing much cooler than normal temperatures for the spring. And that's even lasting into May right now. We're seeing below average temperatures pretty consistently for the month of May. So with these large temperature changes, we get a lot of changes in temperature over shorter distances. You get stronger storm systems. And there are generally cycles of less frequent and more frequent cyclone activity as well for a specified location. So we can not only apply this to the temperature gradients as far as cool season, one season, warm season, the next season, we can also apply this to, I believe, storm frequency. And that again it goes into that discussion on potential versus kinetic energy. Now, higher ACE hurricane seasons, this is my thesis again for my master's, the higher ACE hurricane seasons versus lower ACE hurricane season. What does that mean? Does that mean that the hurricanes, if they're less frequent, there was much more potential energy left over after the hurricane season for that subsequent winter season, or perhaps 2 or 3 winter seasons beyond that? Generally, with a lower ACE during the North Atlantic hurricane season, you're getting excessive buildup of potential energy, posing the question, do extratropical cyclones do their job in redistributing excess heat from the equator to the poles? So vice versa, we can have a very low frequent extratropical cyclone season, specifically nor'easters along the East Coast, and it's an abnormally low season for that one winter. Does that mean they're not redistributing the excessive heat from the equator to the poles? Now, the real challenge in all of this is identifying the spatial, so we're talking about distance as well as temporal, time domains, and how equilibrium is achieved. We live on a big planet, bottom line. Spatially, over what distances do these temperatures achieve equilibrium? A regional scale versus global scale, as an example. Temporally, or time, over what time period is equilibrium reestablished? A summer versus a winter season in the same year, or do we have to wait over the course of years and decades for that equilibrium and temperature to be reestablished? So this is a very important concept. We talk about spatial and temporal domains. Additionally, we must consider timescales over which this equilibrium is achieved. For example, in the summer season, we typically see more localized heating effects, much more higher sun angle, much more intense incoming solar radiation, which heats localized areas, creates these hot pockets. These occur via these mesoscale processes in the summer season, and what we typically get during the max heating time of the day are thunderstorms. And thunderstorms act to redistribute the excessive heat in the low levels of the atmosphere and cause very strong updrafts or upward vertical motion over a smaller horizontal distance, versus synoptic scale processes in the winter season where we get much larger storm systems covering a much larger area. Now, when the thermal imbalance is too great, all right, so let's just say that thermal balance is so great the atmosphere has to get explosive to a certain regard, specifically over smaller distances. And this is when we see severe weather events such as severe thunderstorms, tornadoes. During large-scale synoptic systems, on the other hand, and hurricanes, that generally represents a greater spatial area over a longer period of time. So again, temporal and spatial is the main point I'm getting across with this third bullet. When the temperature changes occur over very short time periods, and they're generally too great for gradual equilibrium to be achieved, the atmosphere is going to get explosive. And that's when we see some of these very, very destructive weather events. So let's now take a look at summer temperature anomalies, followed by the subsequent or following winter temperature anomalies. And let's see if we can come up with some type of idea between these two seasons, taking into account the laws of equilibrium or thermal balance. We'll start off first with the warm summers and the following winters. And what I did is I took some of the more drastic warmer summers and the following winters, and I took the more drastic or large temperature anomalies in the cooler summers and in the following winters. So we'll first start with the warmer summers and the following winters and what happened with the temperature anomalies. We'll start off with 1983 summer season. This is the month of July on the left, orange coloring indicating above normal temps, blue and green and purple below normal temps. And you'll notice in July of 1983, we generally had the warmest air or the higher the normal temperatures over the Midwest and the upper Midwest and the Midwest, the Ohio Valley. And then over here on the right, we show the temperature anomalies for August 1983, and it heated up pretty substantially here between July and August of 83. Notice these anomalies, this bright orange coloring here over the Central Plains up to the Northern Plains, even stretching east toward the Midwest and the parts of Iowa, where temperatures were on the order of 5 to 8 degrees Fahrenheit above normal in this brighter orange coloring. So above normal temps, July and August 83, it was a fairly warm summer. What happened in that following winter? Isn't this interesting? Here is the December 1983 anomalies on the left, the purple coloring indicating the greatest cold anomalies. And notice, look where August had the greatest warm anomalies. See this? Northern Plains, right to the central U.S., Southern Plains, right to Missouri, Iowa, and Illinois. And what happened in December of 83, that winter? This replaced it. Same area that was well above normal in August is now well below normal in December. Colder than normal temps continued right on into January 84 by this green shading. It was fairly widespread, Texas all the way northeastward to Ohio and also along the eastern seaboard in January of 84. By the way, I will mention that this particular 83-84 winter season was a La Nina winter season. Let's now turn our attention to the very hot 1995 summer season. In fact, this was so hot right here in the Midwestern U.S., eastern Iowa, northern Illinois, southern Wisconsin, right over eastward to the lower portions of Michigan and Indiana. This resulted in one of the more deadly heat waves that you'll see, not particularly in August per se here, but in July. So this is actually the month later here on the left, but showing you how much above normal things were in the Midwest that summer. And look at the cooler than normal readings across the Pacific Northwest as well. But in July of 95, Chicago had a deadly heat wave, and it resulted in 739 deaths. The Midwest remained well above normal, like I'm showing you here, into August the following month. Here were the July days and just the maximum temperatures, specifically the 12th to the 15th of July. High temperatures range between 99 and as high as 106 degrees Fahrenheit. Now, this is not the heat index. This is just the air temperature. Really impressive stuff. And even more impressive are these minimum temperatures. Look at this. 12th to the 14th of July, 1995 for Chicago. The low temperatures range between 76 and 84 degrees Fahrenheit. So there just really wasn't much of a break of a cool down. Now let's move on to the 1995-96 winter season. So we saw this in the summer in 95. By the time we got to December of 95, things changed. Above normal in the summer, August in particular here, by December below normal. Notice the green coloring here. Look over here on the right, January of 96, much below normal across the northern plains on the order of 10 to 15 degrees Fahrenheit below normal. And much of the U.S. was in this blue shading, especially east of the Rockies, indicating below normal temperatures. And again, 95-96 was also a La Nina winter. 2011 summer season, you kind of see by the brighter orange coloring where the hottest temperatures were. Now this was June of 2011 on the left. Right over northern Texas and Oklahoma, they had the hottest readings, 5 to 8 degrees Fahrenheit above normal. Some of those warmer than normal readings spread east to the southeastern states up to the mid-Atlantic. And over here on the right, in July of 2011, the bullseye remained pretty much over the southern plains. Oklahoma City, right on north to Wichita, Kansas City, 5 to 9 degrees Fahrenheit above normal in this area. So what happened the following winter? Nothing. No change. Another, the mild temps continue right to the winter season here in this example. Notice that, those areas that were well above normal across southern plains here for June 2011 and July 2011, they are near average now. So no significant change in the temperature anomalies. So despite that warmer than normal summer conditions remain mild across the eastern U.S. Look at this, January 2012, where's wintertime? Not really much to be seen here. So thermal equilibrium in this case did not occur between summer and subsequent winter. And this was a La Nina winter as well, the 2011-2012 winter season. So there are some cases where, you'd expect it to be above normal during the summer and cooler than normal in that same location in the winter, but that was not the case in the 2011-2012 winter season. The 2012 summer season, that following summer, notice what we got here. The warmest temperatures across the Midwest, right up to the upper plain states, as well as East Montana. Nice little bullseye here of 5 to 8 degrees Fahrenheit above normal temperatures over the Midwest and northern plains. And then the 2012-23 winter season, again, not much change. It remained very mild across the eastern U.S. in December of 2012 and also remained mild during the east in January of 2013. The below normal temperatures are out here in the western U.S. in January of 13. Let's go back. Yeah, it really wasn't much of a hot spell. The mean temperatures for July 2012 out here in the west, and then it's much colder during January 2013. So really no correlation there. By the way, 2012-2013 winter season was an ENSO neutral winter season. Now let's look at the cool summers following winters. The 82 summer season was quite cool, especially when we look at the month of June here. Green coloring indicating 5 to 10 degree Fahrenheit below normal readings from the Midwest to the Minnesota area down to the central and southern plain states. And then over here on the right, this is August of 82, staying fairly cool in the east, specifically New England, on the order of 3 to 6 degrees Fahrenheit below normal. What happened in the winter? That following winter season, much above normal. So this would be a case here. You see this in June of 82, how cooler than normal the temperatures are in the green shading here in the center of the U.S. And then boom, by December 82, we're talking readings in the order of 7 to 8 degrees Fahrenheit above normal from Illinois, eastward to Indiana, lower Michigan, Ohio, down to Kentucky. And then over here on the right is February of 83, and look how much above normal conditions were in February of 83 across the northern plain states. Brown shading indicating 9 to 11 degrees Fahrenheit above normal for the Dakotas and eastern Montana. By the way, the 82-83 winter season, that was a very strong El Nino winter, by the way. So here's kind of what you can get out of it, the overall summary. Generally cooler than normal temps here in the summer, June 82, much above normal temperatures in the December 82 timeframe. Looking at 1986 summer season, we saw milder than normal conditions, slightly milder than normal across the mid-Atlantic to the Gulf Coast, right up to the Midwest. And then we saw much below cooler temperatures by the next month, August of 86. Look how much cooler than normal things were, specifically centered on the Midwest in August, on the order of 3 to 5 degrees Fahrenheit below normal. Now, what about the 1986-87 winter season? If we look at all 3 months of the meteorological winter, December of 86 on the left, January 87 in the middle, and February 87 on the right, it were cooler than normal temps, mainly occurring along the Gulf Coast to eastern seaboard in all 3 of these winter months. And warmer than normal temperatures really seem to stay right around the northern plain states in the upper Midwest for that winter of 86-87. By the way, there was a moderate El Nino in this particular winter season. Moving on to the 1997 summer season. I noticed the blue coloring and the green coloring here, June and August. June on the left, August on the right of 97. June and August were cooler than normal across the southern U.S. You distinctly see that here, all the way to the East Coast. Now what about the following winter? After a cooler than normal December on the Gulf Coast and East Coast here, this is December here on the left, 97, the pattern changed to much above normal conditions, warmer than normal across the northern plain states and the northern U.S. in general by February of 98. And this particular winter also was a very strong El Nino winter, the 97-98 winter season. Looking at the 2004 summer season, we saw cooler than normal temperatures. This is June on the left, July in the middle, and August on the right of 2004. We saw cooler than normal temps just invade the U.S., a large swath of the U.S. during that summer of 2004. The following winter, things flipped. After a cooler than normal December right here in the east, here on the far left, the pattern changed with a milder winter setting up for both the months of January here in the middle and February of 2005 on the right. So this particular winter season had a weak El Nino in the 2004-05 winter season. So sometimes these correlate, cool summer, warmer than normal winter. Other times you get warmer than normal summer, cooler than normal winter. Here's 2014 summer season. Showing July in the middle here, particularly July 2014, particularly cooler than normal in the green shading here across the Midwest, the central U.S. And then those temperatures spread to the East Coast over here on the far right by August of 2014. What did the winter look like? Whoa! 2014-2015 winter season. Generally milder, above normal December there for many. And then over here in the middle, January 2015, things got progressively colder for the eastern U.S., specifically New England, 5 to 7 degrees Fahrenheit below normal. And then things became downright frigid by February 2015. This purple shading, we're talking temperatures in the order of 12 to 14 degrees Fahrenheit below normal. Now, purple shading up here in New England, in New York State specifically, temperatures 14 to 16 degrees Fahrenheit below normal for the mean temperature in February of 2015. By the way, this particular winter season featured a weak El Nino. So in summary of tonight's video, we examined a total of 9 cases here. I took some of the more extreme cooler than normal summer months and warmer than normal summer months, and then looked at the following winters. Specifically, I took a look at 4 warmer summers following winters, the following winters after those 4 warm summers, and then 5 cool summers in the following winters, going back to 1980. So I examined 43 years of data. My research is based solely off the temperature anomaly patterns, so I didn't really delve into the precipitation anomalies in this particular video. Referencing the laws of thermal equilibrium, we would expect some sort of relationship or connection to occur from one season to the next. But again, the time scale, that temporal and space-specific locations, the spatial domains vary. For the warm summer following winter cases, we saw that 2 of the 4 cases, 50%, matched up quite well with a warm summer followed by a colder than normal winter. And for the cool summer following winter cases, we saw 3 of the 5 cases, 60% matching up with a cool summer, followed by a warmer than normal winter. Now, other climate drivers such as El Nino, the La Nina, so the ENSO phases, the stratospheric polar vortex strength and location, the North Atlantic Oscillation NAO phases, whether they're positive or negative, the MJO, Madame Julian Oscillation phases, PNA, Pacific North American pattern phases, and anomalous ocean temperatures all alter the results from what we would typically expect to see. These can all be very powerful influences for the winter seasons. Now, the redistribution of thermal imbalances may cover a large geographical area, ranging from regional to global scale. And additionally, we see oceanic circulations. We cannot leave those out. They play a significant role in reestablishing equilibrium or redistributing excessive heat from the equator to the poles. Specifically, I look at 2 currents, the Kuroshio current in the western North Pacific Ocean, as well as the Gulf Stream current in the western North Atlantic Ocean. And as we worked our way from 2010 onward, we did notice one specific trend, and that was for above normal temperatures in the winter season. And this may be a result of human-induced global warming, lots of CO2 levels increasing in the atmosphere. Now, we have seen in the past how longer timescales also, such as decades, come into play as far as warmer or colder periods. So sometimes these stretches of cooler or warmer than normal temperature periods, they go for decades. An example of that would be the late 1970s featured bitterly cold temperatures in the winter seasons, while the 1990 winter seasons were much warmer. Now, winters tend to be warming most drastically as compared to the other seasons. We definitely looked at that in the research across the mid-latitudes. US and Europe, winters are warming most drastically as compared to the other seasons. Overall, you have higher carbon dioxide levels, CO2 levels, which may be skewing data, contributing to warmer temps throughout the year. So, I mean, if we look at the 1980 temperature anomalies, right, and compare them to the present time, we will see that the 1980 featured, around that time period, featured much cooler oceans, also have much lower carbon dioxide levels. Let's take a look over here in the bottom right, the graphic here. These are carbon dioxide CO2 levels from Mauna Loa Observatory in Hawaii. And notice over here in 1980, about right here, about right in there, generally we saw CO2 concentration parts per million, just over 300 parts per million. Now, present day, we have much warmer oceans, and oh yeah, look at this curve, the Keeling curve here. Look at how much higher these CO2 readings are, over 400 parts per million for CO2 concentration per the Mauna Loa Observatory. Now, this was last updated on the 17th of May, 2023, so not that long ago, but you definitely see the steeper slope here to the CO2 levels, basically from this would be about 1960 right to present time. And so it's kind of like comparing apples to oranges. You know, you look at 1980, the temperature anomalies in the summer or winter months, and you notice one thing, that the ocean temperatures weren't quite as warm as they are today, and the CO2 levels are much warmer. So it's hard to really compare certain levels of data to present time, being that we have these CO2 levels much higher today. And specifically, since 2010, we've seen quite a string of above normal winters across the eastern U.S. Quite frequently. All right, that wraps up my video this evening. I hope you enjoyed it, and I covered the interesting question, does summer predict the following winter season? All right, that wraps everything up tonight, everybody. Until next time, everybody, take care. God bless everyone.